Welcome to this presentation on building portable GraalVM Cloud Native applications with Micronaut. For those of you who don't know me, my name is Graeme Rocher. I'm an architect at Oracle Labs. I lead the team at Oracle Labs. We're about a dozen people. We contribute to the Micronaut framework, and we work with the GraalVM team on a daily basis on making GraalVM better. And you can connect with me on social media via those links. And for the demo code today, I recommend you, if you want to get access to it, you scan the QR code. That will take you to the demo application that I'll be presenting in this demo, which demonstrates multi-cloud deployment, multi-cloud application design. So the point of this talk is to hopefully give you some clues and hints on how to build applications so that they remain cloud portable. We're going to be using Micronaut clearly, but I think most of the concepts in this talk you could apply them to Spring or another framework because they're it's general. I wanted to tackle the problem of how we design applications, right, for a multi-cloud portable future where you may be deploying to Oracle Cloud, to AWS, to Google Cloud, the same application and making the most out of application resources. What I'm not going to cover in this talk is deployment, because deployment, the sample application actually does let you deploy, and you can deploy your application to two different clouds. But the point of this talk is more to think about how we design applications so that they remain cloud portable, so you're not coupling yourself to the cloud. And the sample application, which we're going to walk through, demonstrates that. But before we start, let's have a walkthrough of what Micronaut is and go through an introduction. So the Micronaut framework is a relatively new modern Java framework that began back in 2017. And we had the benefit of utilizing knowledge that from 15 years of building Grails and Spring applications and starting from scratch and thinking about how we can solve problems in terms of modern application development, modern application challenges, so microservices, serverless, and so forth. And what we really wanted to address was the kind of heavyweight nature of many frameworks, that were designed to be deployed to traditional serverless containers. And we spent a lot of time optimizing performance, optimizing startup, and looking into how fast Java applications start, how much memory they consume, and designing a framework that's highly optimized by moving all of the logic of the application that makes it work, that makes, for example, dependency injection, configuration management, everything into the compiler. And it works by using Java annotation processing for Java, but it does support multiple languages, so it supports Groovy and Kotlin and other things. Plugs into the Java compiler and computes classes that know how to perform the same tasks that you would imagine in like a Spring application or a CDI application, things like transaction management or AOP, dependency injection. They all work in Micronaut, but everything being computed at build time. But you can also think of it as a general purpose application programming model. So you can actually build anything with Micronaut. Now, obviously, the name, you probably think, oh, I can only build microservices with Micronaut. But that's not the case. With Micronaut, you can build anything that has a static void main. So we have people that are using just the dependency injection part of Micronaut, and they're using it because they're building a Java effects app or a Swing app or a command line application. And we have a very strong link to serverless. So a lot of Micronaut users are using Micronaut in particular in combination with GraalVM to build serverless applications because it improves the cold start performance, and so on and so forth. So how does Micronaut work? Well, basically, as I said, it takes your source code, and we do source code analysis, and during the source code analysis, we generate additional bytecode. Now some people have asked us, why don't we, generate more source code? And a lot of it is because we want to generate tight bytecode that is optimized and efficient, and that shouldn't be fiddled with by our users. But it's also because we want to support multiple languages, right? So if we were generating Java source code, that would complicate the lives of Kotlin users or Ruby users, right? So we use bytecode generation. We process your source code, and whenever you have like a declaration of like what you would think of as a bean or a Spring Bean or a CDI component, what happens is we generate an additional class that knows how to wire that together. And throughout the framework, there's zero reflection, no reflection used at any of the framework level. No runtime proxy generation, so we don't generate runtime proxies. There's no need for libraries like ByteBuddy, CGlib historically. There's also no dynamic class loading, so everything is loaded by the system class loader, which really helps debugging. I spent far too much of my time debugging class loading issues in servlet environments, whether it be Tomcat or JBoss or whatever, because they have all these crazy class loaders that just support features like redeploying applications, which is like not needed in modern Java applications. And all the class path scanning is eliminated because the processing is happening during source code analysis. So we don't need to scan the class path. Everything is pre-prepared. We don't need to look at the reflective data because we compute all of the annotation metadata at compilation time. So what is annotation metadata? Annotation metadata is like, how a framework like Spring and CDI, if you've ever used them, where you can have like, obviously you have an annotation, and sometimes they can have annotations on them, like what's called a meta annotation. So an annotation can be annotated with something else. Or sometimes in a framework like Spring or CDI, you need to know, whether an annotation is annotated on the superclass method. So you have to index all of these annotations, right? And we index all the annotations and compute everything during compilation, which means we don't have to perform the runtime analysis. This is what Micronaut, we talk about when we're talking about build time computation. And the net result is something that's much lighter weight at runtime. So smaller, lighter, more efficient at runtime. And that was the goal. The goal was, to create a framework that had the same kind of productivity, the same developer experience, the same as traditional frameworks like Spring and Grails, but with a more efficient, smaller, lighter weight runtime. And then shortly a month after Micronaut was first open source, GraalVM was open sourced, right? And as it turned out, Micronaut has since then had a relationship with GraalVM, particularly the native image technology of GraalVM, that is very, very strong. And the reason is because GraalVM essentially needs to perform, at least the native image tool, a closed world static analysis of your application to find all the reachable paths. For those of you who haven't heard of GraalVM, it's a drop-in. It can be used in JIT mode to run your Java applications faster, and it's a drop-in replacement for the regular JDK. But it also comes with a ahead-of-time compilation for Java. So in the previous talk, if anybody was here, then, it was covered in detail how it can take Java applications, perform a closed-world static analysis, and produce a native executable for the platform that you're running on. It also has a truffle language framework for implementing other languages. But the main relationship with Micronaut is this ability to take Java code and either run it in JIT mode or produce an AOT image. And when you take a Micronaut application and you compute it into a native executable with GraalVM, the numbers are incredible, right? So you have this super fast startup time. You have, which is orders of magnitude faster. You have much lower memory, right? Consumption, and the reality is that Native Image has allowed Micronaut applications and Java applications, not just Micronaut applications, Java applications in general, to go places that were actually technically impossible before, right? So now, Micronaut, for example, is a valid choice for building serverless applications because, the cold start problem is solved. Now, you can deploy Micronaut to IoT devices on, Raspberry Pi, for example, and it doesn't consume a whole bunch of memory. Those are use cases that weren't a possibility before, right? So command line applications. People are building command line applications with Java again, right? So there's a whole bunch of possibilities that this combination opens up. And because with GraalVM, what you have to do is essentially tell it, if GraalVM fully supports reflection, fully supports dynamic class loading, fully supports all those features, but you have to tell it about it beforehand. You have to say, this class is loaded dynamically. This class requires reflection. This class, and because Micronaut doesn't do any of those things, it's just simple for it to handle, right? There's no configuration supplied. And there's various approaches you can go down to achieve compatibility with GraalVM. The approach that Micronaut has chosen has been to say, we're just not going to do reflection. We're just not going to do dynamic class loading, and that means things just work, and that they work also when you build libraries. So if you use other frameworks, for example, if you build a library, it's not automatically going to be native image compatible, right? You have to take careful care to make sure that you craft it in a certain way to make it. Well, so you build a library, you share code amongst your team, it's automatically compatible with GraalVM Native Image. The only challenge that still remains is third-party libraries, right? So Micronaut does ship with support for the most popular third-party libraries. The most common ones: databases, Kafka, RabbitMQ, messaging system, MQTT. All those things work because we provide additional configuration for third-party libraries. And it's an area that's still being worked on. But using a framework within the context of GraalVM Native Image definitely helps a great deal. So yeah, and the other thing is that with Micronaut GraalVM, you get a framework and a runtime where the teams are working together, right, at Oracle Labs. And in addition to that, we also, from Oracle Labs, we have an extension pack for VS Code, which is great, and we work with on VS Code tooling to make the whole thing easier. Now, when I did my deep dive, I did my entire demo in the VS Code tooling, and VS Code tooling is awesome. This time, I'm actually going to switch to IntelliJ, for folks can demonstrate that all IDEs are possible. But how do you produce a native image with Micronaut, right? So we have a variety. The default way is to use the build tool, right? And one of the things that we work at Oracle Labs as well is the official native image, Gradle, and Maven plugins. So the Micronaut team works on native image plugins for Gradle and Maven, and those are then inbound by the rest of the community, including the Spring team and so forth, and we've been collaborating and so forth. And it's pretty simple to build a native image once you have a Micronaut application. You just type Gradle W native compile, or in Maven package, and you specify the packaging type as native image. Now, when you run those commands, when you run the first command, that's going to produce a native executable that is optimized for that is built for your architecture of your machine, right? So if I run it here on this Mac, it's going to produce a Mac image that I can't just copy to a Linux container and expect to work, right? So we also provide integration by an extended set of plugins, and these are not part of the official Gradle Maven plugins. They're the Micronaut ones, where you can do Gradle Docker build native, and it will construct a Docker image for you. And if on the case of this Mac, for example, I can build, this is an Intel Mac, I can build Linux containers deployable to the cloud. But typically you would want to run these processes in your DevOps or CI/CD pipelines, right? And build native images in CI. Going back to Micronaut, though, Micronaut is, the target is to support any language, build tool, test framework, and reactive libraries. So we have a lot of integrations in Micronaut. You can at the language level, you can choose Java, Kotlin, or Groovy. For the build tool, you can choose Maven or Gradle. For unit testing, we support JUnit 5, we support Spock, we support Kotlin test. For reactive, you can choose whether you want to use React or RxJava 2. And we support a range of different clouds, right? And that's the topic of this talk. Bit of a history of where we are with Micronaut. Last 2 years we've been working on the Micronaut 2 and the 3 line, and Micronaut 4 is due out now at the end of the year, hopefully. Micronaut 4 will baseline on Java 17, so that's the big change. And we've started investigative work for support for virtual threads and all sorts of things. But the current state-of-the-art, latest release that you want to grab is Micronaut 3.7. And Micronaut features in terms of what it can do. It has dependency injection. It has configuration injection. You can provide configuration in a variety of different formats, from properties files to YAML to TOML. Has built-in validation support, so you can validate your application, and aspect-oriented programming model. What does it look like if you haven't seen? This is the basic Hello World controller. You have a controller, you have a get method, uses very familiar annotation model. If you use the Spring, if you use the JAX-RS. In fact, if you do prefer Spring and JAX-RS, we even support using those annotations because Micronaut at compilation time will translate the annotations to the Micronaut version. So you can add a module to support JAX-RS, and if you prefer that annotation model, and you can declare HTTP clients. This is an example of Micronaut's AOP integration where it uses what's called introduction advice. So at compilation time, Micronaut will actually automatically provide an implementation of this interface that makes a HTTP client call. And the declarative HTTP client can be backed on to discovery services, and we'll get to that in a minute. You can also build message-driven applications with Micronaut. So you can build message-driven microservices, or you can integrate them into your existing applications to send or receive messages with Kafka, RabbitMQ, MQ2T, NATS, etc., JMS. And we have extensive support for different kind of database access, right? So you can integrate Micronaut data on top of JDBC, JPA. We have integrations with Neo4j, with libraries like Juke, with Oracle Database, Liquid-based, Flywave for database migrations, many different modules that make you can integrate. This is what Micronaut data looks like, and I'll provide a more demo. So you again provide an interface. You can extend from CRUD repository. So if you're familiar with Spring Data, I worked at the beginning of the Spring Data project on Spring Data and Gorm in the Grails world, where you basically just define finders and they get implemented for you at compilation time, right? The cool thing about Micronaut data versus those other solutions is you'll actually get type checking, right? So it'll fail compilation if it can't implement a particular method instead of failing at runtime, like Spring Data or Gorm used to do, or still do. And you can define custom queries, and everything gets implemented for you. We also have support for security, so you can hook into OpenID Connect, OAuth, security rules, JWT-based authentication, basic auth. It's all built into the framework, right? So now let's move on to cloud native applications. So what does it mean for an application to be cloud native? Well, a lot of folks talked about adhering to the principles of 12-factor applications. You can go over there and check that out. But basically, What you want to do is separate configuration from your application and avoid coupling to your environment, right? So generally, it's in the cloud vendor's interests for you to place logic in your application that couples you to a particular cloud. You generally don't want to do that. And you should try and use abstractions and interfaces where appropriate when interacting with cloud-specific APIs so that you can keep your application portable, not just for production purposes, but also so that you can keep your application testable. This is a very big bugbear of mine where you see lots of code written and you can't no longer run the app locally because you need to connect up to the cloud or whatever to actually run it, right? And another thing it means to be cloud native at the application level for me is to maximize the observability of your application. It's critical observability when you're building microservices to be able to get insight into the way your application is functioning, whether it be metrics, whether it be tracing, whether it be any kind of insight into the functioning of your application. And it's important to be able to automate deployment and releases, right? So I mentioned CI/CD pipelines. You should use those, and you should do continuous deployment, right? Now, on the deployment side, there's a range of ways to do deployment, and that's not the subject of this talk, as I mentioned. You can use Kubernetes. You can use, for deployment for your production environment. You can use VMs. You can use whatever. And there are tools for automating a lot of that deployment, whether it be things at scale, things like Spinnaker and so forth, that exist within the cloud native community. What I'm focusing on is how you design your application, in particular with Micronaut, but I think it's applicable to other frameworks as well. So in general, in Micronaut, there are abstractions for cloud native services, so services that are provided by your cloud. We have the ability to send traced information, right? Whether it will open telemetry, Jaeger, or Zipkin. You can integrate Micronaut with service discovery and distributed configuration. So whether you're using console, Eureka, or Kubernetes, config maps and service definitions, you can integrate those into Micronaut and have, for example, in your Kubernetes environment, service discovery automatically work with client-side load balancing and load balancing inside your Kubernetes cluster. It'll integrate with config maps, etc., etc. Monitoring, right? This is where we get to observability. You can integrate it with Micronaut. We have full support for Micronaut so that you can export metrics from your application, and you can add additional observability via JMX if you need to, etc. API development in the cloud, you often need to expose different types of APIs, whether it be GraphQL, gRPC, and open API definitions for how all of those work. You saw some of it already with regards to containerization. So we have strong support for Kubernetes, but also for test containers. Often when you want to write integration tests in the cloud, many clouds provide you with emulators or things like local stack on AWS. Test containers integration in the framework helps a great deal with that, as does the fact that you can build Docker images with the framework automatically. And then we also provide abstractions over various cloud services. So a lot of clouds have caching services, they have email services, object storage, database, etc. And for each of these, there is a way to write your application without coupling you to the cloud service. Each public cloud has an API that they expose, an SDK, and it's very easy to import the SDK and write all your application and couple it to the cloud SDK. But that does kill your cloud application portability if you ever want to move it to a different cloud, or often maximize the cloud resources available to you, right, and deploy it to multiple clouds at the same time. So in general, you should try and avoid vendor lock-in where possible. And now we're going to get to the demo part. So I just want to point out that if you want to create your own application that is similar to this one, you can get started, and you can go to Micronaut launch to do that. So launch.micronaut.io, and all of the features that I demonstrate in this demo are available from you can select open telemetry or whatever integration that you want by clicking the features button. generate your application and then push it to GitHub, and you can start developing straight away. You can also create an application with the command line, but this is an optional extra. We have a command line that you can install via SDK man. You can install it, but it's not needed to actually use Micronaut. It's just a nice extra thing to have. And you can also create applications via either IntelliJ IDEA Ultimate or VS Code. So both VS Code and IntelliJ IDEA Ultimate have integration with Micronaut launch, so you can create applications directly from the UI of the tool. So in VS Code, it does the same. It takes you through a wizard, and you can create your app directly from the IDE. Okay, so let's look at a demo. So over here, I have a Micronaut application, right? And it's structured in a very different way to a traditional Micronaut application, right? So this is what I mentioned when you start to think about like multi-cloud development. Like, how do I build an application that is not coupled to a particular cloud? So here I have it's essentially a multi-project build. And over here I have my app directory with source main Java. And in here I have my application code that is not related to any particular cloud, right? So I can come in here, and this is my entry point for my application. And there's some useful things that are interesting to look at. For one, I set up a default environment that is called dev. That allows me to load up a extra configuration called application-dev.yaml that is only active when I'm in development, right? This is the default environment flag, right? So Micronaut has this concept of environments, and if you specify them a default one, if no other environment is active, then it'll activate the dev environment and allow you to provide configuration for just your development environment. Other than that, this is a regular Micronaut application, and I'm going to run it, and we're going to have a look. It's using an in-memory database, and if we go to the URL, you get basically a list of people. And my UI skills are not amazing here, but as you can see, it's a very simple app. And you can click on a person, and it says "Hello, Graeme," right? So it's a pretty simple app, right? So let's look at how this works, right? So there is a person controller, and the person controller uses Micronaut's dependency injection facility to inject a few other components of the application: a message service, a person repository, and object storage operations, which is from one of the Micronaut modules for object storage. So you can see in the imports of this application here, there's nothing specific to any cloud, right? There is a list method, which is mapped to the root URI, which uses my repository definition to find all the people. The repository itself is using Micronaut data, so it's a simple CRUD repository where we have dialect set to H2. So that's another interesting thing. Now, generally it's better to use the database that is most similar to your production environment, right? But I wanted to demonstrate here is how you can deal with the case where you have different databases in different cloud environments. So this is a JDBC repository that is using an H2 in-memory database. And we have another method down here, which will basically look for a person by ID and render the person and retrieve a message for that person. And this calls the message service. This is the message service. And there is a default implementation, right? And this is where things get interesting. So we have a default implementation here that just says, hi, person.name, right? So that's that message here, hi, Graeme, right? So this implementation gets activated only when no other implementation is present. So we declare @requires missing beans equals message service. So if no other bean is present, this implementation is activated. And we use the same approach for object storage. So here, if object storage is missing, I'm just going to read data from, instead of using a cloud object storage service, I'm just going to read data from my class path. So it starts pulling images, just from my class path for local development. This means that I can keep the application decoupled from the cloud, and I can run my tests and stay, very productive. Test execution is fast. I could integrate it with test containers if I was using something else. But basically, the application here is completely decoupled from anything related to the cloud. We just have configuration for running the application locally, right? But if we drop into one of the other subprojects, so let's look at the AWS module, for example. The AWS module, what it does is it depends on my core code. So in the build configuration, it adds a dependency on my app module, excluding the H2 driver because I don't want that in production, right? So remember, a lot about like optimizing your application for the cloud is making sure that you have just the minimal set of dependencies to deploy to that cloud, right? It then starts to add integration with the cloud that I'm running on. So we add, for example, the SDK, which is needed by many of the other services. We start exporting metrics to CloudWatch, right? So Micronaut will plug in your metrics export to AWS CloudWatch. We enable tracing by adding new dependencies to my application for OpenTelemetry that plugs into AWS X-Ray and AWS. And suddenly I start getting distributed traces for my application being exported to the AWS infrastructure just by adding a few dependencies. We added an object storage implementation that backs onto Amazon S3, right? So the same code that was reading and writing from just my local disk starts using Amazon S3. We added dependency to make sure that any configuration in my application is read from AWS Secrets Manager, right? So we've defined here that I'm going to use AWS Secret Manager to read all of the configuration from my application. And because we're using Amazon RDS with MySQL, we add database dependencies for MySQL. So let's look at the sources for this application. So here we have, there's not many changes. We have an AWS application which activates the Amazon EC2 environment, but this is just a string. It could just be AWS, right? It activates that environment, the Amazon EC2 environment, and that causes extra configuration in my application to be loaded when it's executed on Amazon EC2. The configuration enables things like specification of an AWS S3 bucket. It enables export via configuration to CloudWatch, so I configure where the namespace of where I want to send my data in CloudWatch. It enables the configuration for RDS, but notice here as well that I'm not hard coding any passwords because all of those are stored in AWS Secret Manager, right? Nothing is kept insecurely in my configuration. This is all looked up dynamically and stored in secrets that get populated. I get to configure my tracing as well. So this is cloud-specific configuration. I have configuration that is specifically for my deployment to Amazon AWS, right? I also have a database migration that's specific to that deployment because here I am deploying with the MySQL database, right? And to make sure my application keeps working with AWS, I replace the repository that was specified to use H2 with a MySQL version. So this is where dependency injection and dependency injection systems help you adapt to the cloud, right? Because they allow you to replace components in your application at runtime and wire your application differently for a cloud, right? Without a framework and dependency injection, it's very, very difficult to make your application cloud portable. Like the naive solution would be to put all of the dependencies in a single app and make your application this one big bloated mess where I have all these dependencies and in order to export data to the cloud, right? And I also have a AWS message service which requires the Amazon EC2 environment, and when it's activated, it says, "Hi, welcome to AWS." Right? So we have a different message service when I'm running on AWS. This is just for demonstration purposes, right? And the same thing with for OCI. So if we look at the Oracle Cloud version, again, we have a different build or Gradle, right? Same thing, excludes the H2 dependency. activates Zipkin tracing, exports data to Oracle Cloud monitoring, uses Oracle Cloud object storage, basically use Oracle Cloud ATP, so an Oracle database, the SDK, and stores secrets in Oracle Cloud Vault, right? So I'm altering my dependencies for deployment to a different cloud, but I'm not changing my application sources, right? And you know, I have an OCI service that says welcome to OCI. I have a different database, so I have a different schema that gets migrated for Oracle. And I have a different configuration, which is application-oracle-cloud.yaml. So this is a different configuration for specifically for that. So with the structure, I can structure my application in a way where I can make sure my common code is decoupled from the cloud, but I can also add you know, tests for my individual clouds, and you can see that I have an application test.yaml here that will actually activate test resources and test containers, right? So you know, and then when I get to the deployment part, you know, I can CD into OCI, and again, you know, we have an OCI. If you want to try this demo, you can basically run terraform.apply for Oracle Cloud. It only uses free tier resources, so you won't pay anything. Or you can CD into the AWS version infra project in this project, and you can run CDK deploy. I think it is, and it uses AWS's CDK and only uses free tier resources to deploy the application. So you can try this out with the sample and try it out. I'm not going to do it because it actually takes between 10 and 15 minutes to actually deploy the application. But what you get is two different applications. So we have, for example, the AWS version here, and we click, which is running at this IP address. And you can see, welcome to AWS, right? Welcome to AWS, and we can go the Oracle Cloud version, same application, but this time, welcome to OCI, right? So the application is adapted to the environment. And when you go into the Oracle Cloud Console, for example, and you go into Trace Explorer, my application has been connected up with Oracle Cloud, you know, Trace Explorer for Zipkin, and you can see all the traces appearing. Same thing if I switched over to AWS CloudWatch. The application has been integrated into the AWS X-ray metrics and all of that, and I'll get traces and all that kind of thing, and trace data from AWS. Sometimes it takes a while to appear, but basically you get trace information integrated, you get metrics into your application, and it's all a matter of just specifying a little bit of cloud-specific configuration, right? So this is where you say you need a framework to be able to integrate things into the cloud, and in terms of those are the native image versions running, but you can build the application into a native image. So I actually have the native image version built up, pre-built, but basically the native image application of this. Whoops, I already have it running, I guess, somewhere. Did I run the application somewhere? Yeah, I have my application running. So just kill that. And you can see that the native version of the application, the same application, but optimized natively, with a super fast startup time and low memory footprint. So that is more or less the demo. I suggest you go and try it out. Whoops. I don't know what's happened there. Okay, play from current slide. Okay. The demo code is available at this QR code. So I recommend you scan that QR code and check out the sources. You will be able to see how you can take that application. Provide if you have an AWS account, you can scan. You can enter it. Just configure. Just provide a little bit of configuration to set up the local SDK. And in Oracle Cloud, you have to provide in the Terraform variables your component ID. There's two things to configure, which are all documented in the README. And you can take the application and deploy it to multiple clouds and check out how it essentially is possible to build applications that are decoupled from the cloud, that basically can remain cloud portable and remain testable locally with Micronaut, providing all of the plumbing and the wiring to make sure things like connecting up to the database in the cloud works, or exporting metrics, or sending trace data, or looking up secrets in Oracle Cloud Vault or in AWS Secret Manager. So some tips in summary: use multi-project builds with a new sub-project per cloud to avoid bloating your application dependencies. Programmed interfaces and ensure loose coupling through dependency injection to avoid hard-coding logic that couples you to a particular cloud. Externalize your configuration and secrets, decoupling your application from the environment. Never hard-code passwords and everything into your configuration. Make sure you use secrets lookup. Use containerized testing tools like test containers or emulators to write integration tests for each cloud. The sample application, actually, if you run the tests for the OCI module, it uses test containers to spin up Oracle database for the tests. And if you run it for the AWS module, it uses MySQL inside test containers to run the tests and ensure everything is still working. Automate deployment and releases with build pipelines, CI, Jenkins, or AWS Cloud Build, or Oracle Cloud DevOps, whatever. And optimize your applications with native image, which is particularly useful in containerized environments like Kubernetes. And the sample code as well, I would like to have used Kubernetes to use K8s to apply it and do all the deployment, because it probably would have been easier. But for the sample code, I wanted to make sure that all of you be able to try these demos on AWS or Oracle Cloud using just free tier resources. So both of them are just, you can deploy, and you're not going to be charged for anything. Whilst if you have to spin up an OK cluster or an EKS cluster on Amazon, it's much more expensive, right? So thank you very much. If you have any questions, do come and ask them and let me know. Thank you. Yeah.
You deploy with EC2.
Yeah.
But maybe Micronaut, you can also build Docker native image.
Yes.
Would you recommend to go with EC2 or ECS?
So yeah, I mean, if you're building native images, then the container service is better, right? But the question is, you're building native images, and would it be better to deploy to ECS, which is Elastic Container Service, instead of EC2, which is the virtual machine service? So Elastic Container Service would be better, but I wasn't sure if that was a free tier service, so I wanted to keep the demos so that you guys could try it at home and so forth. It deploys it to EC2 for the moment, but yeah, I mean, it is a more user-friendly service, right? If you're deploying containers. If you want to deploy the container, basically you can go into the terminal and you can say AWS Docker push native, right? And this will build the native image into a Docker container and push it to your configured container registry, right? So you can log in beforehand and you can set up your build pipelines. I'm not going to let it run, but you basically push your application to a container registry. Okay. Yeah.
How would you debug the issues that you find in the GraalVM build if you don't have your regular debug?
So how would you debug the native image in the cloud or locally? Right. So locally, in general, with Micronaut, we try to not get people in the situation where they have to debug, because Micronaut should just work with native image, right? However, if you do need to debug, you can connect the latest versions of GraalVM CE and EE. Both support remote debugging, so you can attach a debugger. nowadays, right? But generally, it's never a problem unless you're integrating a third-party library. And if I'm trying to diagnose why a third-party library is not working, it's normally down to the missing reflection config. So, and there's a really nice integration with the Maven and Gradle plugins where you can say Gradle run -p agent, and it will activate the tracing agent. And, and you can just see from the generated config, oh, this is, you know, and rationalize, oh, this is why this is not working, right? Because there's missing reflection config. But if you do get in a situation where you want to debug, then you know there is remote debugging support, and it's actually that's a nice feature of the latest versions of IntelliJ Ultimate and the VS Code tooling that you can remote debug the native image. Yeah.
Do you have experience when deploying a native image for longer running applications? What the impact of CLGC is in
So we had an interesting question, was it a couple of days ago about that, right? Where you know for long-running GPs, and there's interesting research still to be undertaken on different GC strategies. It is true that in native image applications that you have far less CPU utilization in general, and you can configure GC pauses to be shorter with G1. But it'll be interesting to see where that evolves with things like serial GC and so forth. Yeah.
The question when you were showing the example, when you were deploying on AWS, that's actually deploying a container or a Lambda function?
It's deploying a EC2 instance.
And is it possible to switch to deploy Lambda based on the core functions themselves?
Yes, so if we actually have support for Lambda where you can repackage. I should have probably shown that you can basically switch the runtime to Lambda, and you say Gradle will you build Lambda zip, and it creates a zip file for you which you can upload to Lambda and deploy it to Lambda.
But you don't need to modify your code.
You don't need to modify your code. No, you run it. You have to run it behind API gateway, but basically it's the same code, right?
And just a second question, when you were showing the cloud formation on AWS, do you have something like the Terraform support over there for AWS, so I can deploy?
The example, if you grab it, it's using CDK, right? So it's like it's written in Java, and it's like Terraform, but it's Java code, right? But the bad thing is that it's coupled to AWS, right? So you only an interesting research project actually that we have underway is to see if we can create like a cloud portable CDK option. Yeah. Yeah, because the Oracle one we did Terraform, and there's an interesting open source project called Pulumi as well that does, a CDK that's like basically portable across clouds. But there's definitely research to be done in that area. Yeah.
So behind Micronaut is the Micronaut Foundation, right? If I understood correctly.
Yeah.
Can you tell us a little bit about how you guys are financed or what your business model is?
So the Micronaut Foundation is a foundation, so it's non-profit, right? So the business model is investment from different companies that want to benefit Micronaut and the community, right? So today, Oracle and Oracle Labs is an engineering partner in the foundation. So we provide engineering resources and capacity to the Micronaut Foundation, and we have a partnership. And we collaborate with Object Computing, who operate the foundation. But other companies are also foundation sponsors, right? So if you all the information on how to become a sponsor and what it means to be a sponsor is on the website. I would check it out if you go to micronaut.io. You find a link to the foundation there. Yeah. Hope that answers your question. Okay. Well, thank you very much.